The statistician George Box is often cited for his pertinent comment about statistical modelling. He said, "All models are wrong, but some are useful." So what did he mean by this? Every model is some kind of simplification of reality, and we make strong assumptions when we fit them. But while not perfect, models can be incredibly valuable. In public health research, you've seen how we can use them for evaluating interventions, understanding and predicting disease. In the first part of this lecture, I'll take you through the assumptions we make in linear regression and how to check them and how to assess goodness of fit. And in the second part, I'll demonstrate this using the COPD dataset. There are three key assumptions we make when fitting a linear regression model. The first is that the relationship between the predictor and the outcome is approximately linear. The second assumption is that for each value of the predictor variable, the outcome variable follows a normal distribution. If you recall, that's different from the assumption we made when applying the Pearson's correlation, where we needed both x and y to be random variables. And finally, we assume that the variance is constant for each value of the predictor. We can get a reasonable idea of whether or not these assumptions hold for one predictor just by examining a two-way scatter plot. But a better approach is to examine the residuals from the model. From the previous lecture, you'll recall that the residual is the distance between the observed value and the fitted regression line. If all three of these assumptions hold, then the distribution for the residuals will be normal with a mean of 0 and a constant variance across the predictor values. And there are three useful plots we can use. We can first assess whether the residuals are normally distributed by either looking at a histogram of the residuals or, better, a QQ plot. And both of these can be easily produced in R. So here's an example of a histogram of residuals, and this has come from a model with 40 observations. You can see a normal distribution has been overlaid on the histogram. Below it's the corresponding QQ plot for this data. The QQ plot is a plot of the quartiles of the residuals against the quartiles of the theoretical normal distribution. If the residuals are normal, then the observations will lay on a straight line. Comparing these graphs, you can see that the QQ plot is a bit more informative as it better highlights where the two distributions differ. So what do you make of these plots? Would you say that the residuals from this model are normally distributed? In this example, the dataset is quite small, so we'd expect the distribution to be a bit bumpy. And the histogram looks reasonably symmetrical around the value 0 given the sample size, but it's easier to see in the QQ plot that the assumption of normality is reasonable, as most of the values lie on the straight line. You always expect to see some drift in the tails of the distribution of a QQ plot, so the drift we see here is not unreasonable. When assessing the QQ plot, your focus should be on the middle section of the data. In order to assess the assumption of constant variance across the predictor, then a useful plot is to view the residuals by the fitted regression values or the predictor variable. On this plot, the residuals are on the y-axis and the fitted values from the regression line are on the x-axis. So what do you think we need to look for here in this plot? What you want to see is an equal scatter of residual values around the mean value of 0. What you don't want to see is variability in that scatter. So looking at this plot, there's no obvious pattern in variability across the fitted values. And finally, we're also interested in how well the model fits the data. So there's several ways we can do that, and this lecture will look at a statistic called R squared. So let's think about what a regression line does. The regression line will explain a proportion of the variability in the data, and the residuals indicate how much variability is left unexplained after we fitted the regression line. So R squared is a measure of how much variability is explained by the model as a proportion of the total variability of the data. So this means R squared is a value between 0 and 1. In fact, when we have one predictive variable in the model, the R squared value is equal to the square of the correlation coefficient. To get a feel for this, let's look at two examples. You can see that the observations in the right-hand side graph sit closer to the regression line than the observations on the left-hand side. So the line on the right-hand side is explaining more of the variability in the data. If I calculate R squared for each of these models, the R-squared value is 0.15 for the left-hand side, meaning the regression line is explaining 15% of the total variance, compared to 58% for the regression line on the right-hand side example. But we have to be a little bit careful with R-squared, as each time we add a variable to the model, R-squared will just increase. So you may think, what's wrong with that? What's wrong with keeping adding more and more variables to explain more and more of the variation? Well, we have to be careful of overfitting our model. So overfitting is a phenomena where the model begins to describe the random error in the data rather than the relationships between the variables. So R-squared is not a good measure if we want to compare models. But instead, we can obtain an adjusted R-squared. The adjusted R-squared penalises for the number of predictor variables included in the model. So it's a better measure to compare our models with. And we'll look at this in more detail later. Right, that's all for now. Join me in the second part of this lecture, where I'll introduce you to a new data set and we'll put what you've learnt here into practice. See you soon.